Okay, Olivia. You can stand up, but don't approach her. Okay, I need you, so for the final, you should expect the MO diagram. Okay? So the MO diagram would be up to any element up to neon. I need you, right now, without telling me, to pick an element. Tell me when you're ready. And people would be happy if it's one of the ones closer to neon, like boron to neon. Okay? Got one of those? Okay, tell one of your buddies. Is that a real element? Okay. I need you to pick a charge. Okay? Reasonable charge, like 0, +1, -1. Got one? Tell your buddy. Is this real? Okay. You can sit down. Okay, Olivia, I'm going to read her mind now and solve the MO diagram for the element that I don't know. Okay? So we'll call it, we'll just use a variable for now. Let's call it x2. Okay, I don't know what it is, but I'm going to draw the MO diagram for it. It comes from x and x. Okay? And so we need to draw the energy scale. Okay? And then we're hoping for a harder one, so I'm expecting a 2s energy level and a 2p energy level. All right, now I'm going to start to draw out the diagram even a little more by drawing the molecular part, or the part that goes in the center. So there's going to be a bonding and an anti-bonding. Draw that out. Okay? I'll even label it for her. Sigma 2s and sigma 2s star. For anti-bonding, the higher one is always a star. All right. Because a little bit of wires are crossed, and there's too many people in this room that I'm receiving bad energy from, you need to tell me if this is an atom that's oxygen or above in atomic number, or nitrogen below. I don't want to know the element, I just want to know which one. Nitrogen and below. Okay, that's what I thought. At least 50-50 is what I'm saying. So, I'm going to draw this, 2, 1, 2, 1. I'm expecting that for nitrogen and below. And let's connect the dots. All right. And for Olivia, I'll even label this for her as well. Pi 2p, sigma 2p. Remember, the ones with two lines are called pi. The ones with single lines, even like below, are called sigma. So the single lines, like up the very top one, pi sigma 2p star, and the double lines, two lines in a row here, pi 2p star. Really easy to remember which one's pi and which one's sigma. All right. I have now completed Olivia's MO diagram. It's time for her to reveal. Can you stand up, Olivia? Some respect for the MO diagram. Okay. Can you now reveal what was the element or diatomic molecule you were thinking about? Okay, that I was kind of thinking that. Okay, so N2 minus was hers, so that comes from an N and an N minus. Now it really doesn't matter which part I put the N minus on, if it was on the right or the left. Doesn't matter. But one's an N, one's an N minus, so when they go together, they'll make an N2 minus. Alright, well the N, and I'll do this in a different color, is 1s2, 2s2, 2p3. This would be 1s2, 2s2, 2p4. Okay, so I got the electron configurations. Remember, I didn't include the 1s, because that's a core electron, so I don't need to draw it in my MO diagram. Alright, let's fill in those electrons. On the left-hand side, it's 2s2, 2p3. 1, 2, 3. And on the right-hand side, it's 2s2, 2p4. 1, 2, 3, 4. Okay. Now let's fill in the electrons in the middle, in the molecular orbitals. For the bottom picture, we've got 1, 2, 3, 4, or a total of 4. So 1, 2, 3, 4. For the top, for the 2p part, there's 3 and 4, or a total of 7 electrons. So we'll go 1, 2, 3, 4, 5, 6, and there's one more right here, 7. All right, the last part we can do together. What's the magnetism? Para or dia? This is para just because of the one unpaired electron. So we call this paramagnetic. And then we calculate the bond order. What is the first number here? Should write 6 because there's 6 electrons in bonding molecular orbitals. 2, 4, 6. What's the second number? You get a 1 because there's 1 electron in an anti-bonding molecular orbital. So 6 minus 1, that's going to be 5 halves or 2.5. So it's a 2.5 bond. This is one we wouldn't be able to draw with Lewis, but it works well with the MO diagram. And you can see, for her example, I pretty much drew the entire diagram. The only thing I really couldn't fill in was the electrons. Okay, and that's the only thing that really changes. Any questions on this? Okay, there's our MO diagram. Make sure you can do these. Practice them. Make sure you can do them outside of lecture. I would expect for the average person 5 to 7 minutes tops to finish a problem like this by the time we get to the final. Yeah? You will not, in this class, you will not be given anything past neon in atomic number. So no metals. Okay. Unless, well, you could be given lithium or beryllium, those would be metals, but they're not transition metals. Yeah, so nothing above neon for this class. Yeah, there's another question? I don't see you, but go ahead.
What will it be if it's oxygen or above? What's the difference?
Oxygen, fluorine, or neon has a slightly different picture. She's asking about one of those. The picture would look slightly different. It's where the pi 2p and sigma 2p levels will flip. And that's the only difference. Let's see if I have one of those. The only difference is these two levels flip for oxygen, fluorine, or neon. That's up to you to remember. Okay? What do I mean that they flipped? Well, notice these two levels, they're opposite of each other. The pi 2p is on bottom, where over on the right, the sigma 2p is on the bottom. So they're flipped. They're opposites. Okay, that's the only difference. And those pictures are in the reader in the textbook. All right, so make sure you can do those. It should feel like an easy 20 or 30 points on the final. Okay, whatever it feels. Maybe not right now, but by the final, well, it should feel that way. Okay, before we do the other examples, let's do a little bit more. So it's just a little bit more to finish the lecture, and then I need to show you what's coming up. And today, the last check mark. Yes, I will check off the final in the privacy of my own office. So, today we're going to do this. We got to do the evaluations, and we need to do the talk about the final. We're going to do all that sort of stuff. I'll review what you need to know for the final, etc. So lots of stuff to do. Let's get going. Okay. Just to review what you've seen already, for a carbon, which is 1s2, 2s2, 2p2. Carbon, we're taking this as an example because it's a really easy one to look at. Unhybridized from chapter 7, not including the 4 electrons, you would draw this for a normal carbon. Okay? for an energy electron configuration type diagram. This carbon can hybridize. Let me zoom out a bit. Draw a little brace here. It can hybridize in a couple different ways. If this carbon is going to be in a tetrahedral type complex where there are 4 groups, because 4 groups in a tetrahedral complex, it'll hybridize like this because it needs to get the 109.5 degree bond angles. sp3 with 1 electron in each of that hybridized orbital. Okay, if it wants to be in a differently shaped compound, okay, so let's say one that is trigonal planar, okay, trigonal planar, that's one with 3 groups. What's going to happen, because that has a different bond angle, it's going to hybridize differently. Where one of the 2 P's will stay unhybridized and the other 2 P's will hybridize with one of the 2 S's. And there's only one English. So it'll look like that. Those are the 2 things we did last time. There's one more hybridization scheme, kind of like this, that I'm going to show you right now. The last one that we're going to draw out is for the linear shape. Linear. This is where there's 2 groups. This has a slightly different hybridization because linear is 180 degrees. And to get to that 180 degree bond angle, it has to have a slightly different hybridization. And so we're picking up on page 106, 107 of the reader, and of the textbook, we're around page 404, 405. What happens is 2 of the 2p orbitals stay unhybridized, and 2 of them, or one of the 2 s's and one of the 2 p's, the one that's left, hybridize. Each orbital will have an electron. It turns out, if 2 of the 2 p's stay out of it, so 2 of the p orbitals stay out and stay unhybridized, and you take, I'm going to move this for a moment, there's a figure like this in your textbook. One of the s's and one of the p's, you mix them together, they make new orbitals. Those new orbitals look like this, and when you put them together, they make the linear shape. The linear shape of the 180 degree bond angle. And so this is our guess, our model of what's happening when a linear shape comes about. It's actually an sp hybridization to get that linear shape from the atomic orbitals. So that schematically, or the scheme, would look like this bottom one here. Okay? Now, in another color, so those are the 3 we're going to draw out. The top one, an example would be a carbon that has a tetrahedral shape, something like that. A tetrahedral shape has all single bonds, and single bonds are sigma bonds. Okay? So this is going to form 4 sigma bonds. Each hybridized orbital will form a sigma bond. Okay. For the trigonal planar, for carbon, it would look like this. There's trigonal planar. You notice there's a double bond now. Each bond, including the double bond, is composed of 1 sigma bond. Okay? Each one of those is composed of 1 sigma bond. And that's these 3 sigmas here. These hybridized orbitals, as far as we're concerned in this class, will always form sigma bonds. So these 3 will form sigma bonds. That second bond of the double bond comes from the 2p making a pi bond. Okay? So a double bond, and I'll write this out in just a minute, is composed of a sigma and a pi bond. To make the linear shape for carbon, because we're doing this for carbon as our example, carbon's the easiest one to look at first. There would have to be a triple bond there. This has 2 groups. 2 groups, you know, would be the linear shape, so it's 180. It will look like this for carbon. So if it looks like that, to the right and to the left, it's going to have a sigma bond. Each sigma bond just like before, always comes from the sp, or the hybridized orbitals. Hybridized orbitals form sigma bonds. Well, where do the other two bonds of the triple bond come from? Well, each one of these p orbitals forms another bond on top of that sigma. So there's two p unhybridized orbitals. Each one of those forms a pi bond. So let's say triple bond is 1 sigma and 2 pi's. Let me summarize what I just said in a little table at the bottom. And this is also written in a different way on page 107 of the reader. In a much bigger table, I'll make the smaller table here. Bond type. Sigma. Okay, if you have a single bond, that's 1 sigma bond, 0 pi's. If you ever see a double bond, that's 1 sigma and 1 pi. And if you ever see a triple bond, that's 1 sigma and 2 pi bonds. The pi bonds always come from the unhybridized p orbitals. The sigma bonds always come from the hybridized orbitals. Okay? So this is something to know, because we're going to use this to count the total number of sigma and pi bonds in a molecule. We'll do that in a little bit. Before we get there, there's one other table that I want to show you. And it's kind of, I'm taking the table on the bottom of page 107 of the reader and splitting it into two, really. How can you determine the hybridization of any given molecule? It's dependent on the number of groups. So just like in Vesper, you count, say, 3 groups, that's trigonal planar. You count 4 groups, that's tetrahedral. So all the shapes are based on the number of groups around the central atom. And we can have, for our class, it counts from 1 to 6, though. In reality, there can be more than that. Here's how you figure out the hybridization. One group is not really hybridized, but that would just be an s orbital. An example would be a hydrogen with 1 bond to something. The hydrogen would be an s orbital. If you have 2 groups, we did this one. This is sp, that's linear. 2 groups is linear, it's sp hybridized. If you have 3 groups, that's trigonal planar, according to Vesper, and the hybridization is sp2. If you have 4 groups, that's tetrahedral, the hybridization is sp3. For these 3 right here, I drew out the scheme for you. And that's what you saw on the previous page. This scheme here is for groups 2, 3, and 4. Okay, so we did groups 2, 3, and 4. We're not going to do 5 and 6 or anything else just because they're a little more complicated. But in this class, and in OChem, it's typical that you should know groups 2, 3, and 4, how to draw those out. For groups 5 groups, that would be a trigonal 5 pyramidal, 5 groups, and we call that sp3d hybridization. For 6 groups, that would be octahedral, and we call that sp3d2. Okay. Now, this is another one of those that you'll need to know for the final. Let me show you the pattern, though. How many s orbitals are there for a given n? Just 1. So notice the one group has 1 s orbital. After you use that up, it's done. So now, once you go to 2 groups, notice we add the next orbital, p. How many p orbitals are there for a given n? 3. So that's why it goes sp, sp2, sp3, and then we run out of p orbitals. So thus you go to the next orbital, that's a d. So you notice the next one adds the d in there in its hybridization. And then d2, and you could guess what the next one would be, sp3, d3, etc. So that's the pattern here. And this table, along with this table, if you think it's something you're going to forget, I would write this out on the last page of your final before you start the final, and you can refer back to it when you need it. Okay? These are true, and I'll show you how to use them in just a minute. Okay, a couple more things, and I'll kind of refer back to this picture for a second. So, single bond is made of a sigma bond. Okay? Sigma bonds are the strongest. A double bond is made of a sigma and a pi. So it's not twice as strong because pi bonds are weaker than sigma bonds. The reason is, and I'm not going to draw it out for you right now, but pi bonds break upon free rotation around the axis. So if you rotate the molecule, you can break a pi bond. They're relatively, compared to sigma, it's easy to break. So a double bond is stronger than a single bond, but it's not twice as strong because it's not made out of two sigma bonds. It's a sigma and a pi. Likewise, a triple bond is not 3 times as strong as a single bond. Okay? So that's just something to know about sigma and pi bonds. Okay. All right, let's try some of these examples that I have here. Believe it or not, this one is slightly easier than others. I just made up a random molecule that looks ugly so it would scare you, but it's not a scary problem. Okay? I guess you have to trust me. Okay, we're going to try to determine the hybridization of each atom. So let's try that. Okay? What you need to do, you want to get out, spin this around, this table. Okay, we're going to refer to this table right here. All right, let's go out. Okay, so what we need to do in order to find out hybridization is count the number of groups around an atom. So let's start with hopefully some of the easier ones. I'm going to start right here. Help me out. How many groups are around that carbon? You should see 4. There's 3 single bonds from carbon to hydrogen. That's 3. And then 1 single bond to the right to carbon. That's 4 groups. What do we call that hybridization? 4 groups is called sp3. Refer to that table. sp3. How about the next carbon over? How many groups? All right, I've heard every number. One of those was right. There's 3 groups. The carbon has a single bond to the left, a double bond to the right, and a single bond to that hydrogen that's on it. That's a total of 3. 2 single bonds and a double. We call that what? sp2. Next carbon. How many groups? 2 groups. A double bond to the left, double bond to the right. We call that sp. 2 groups. It's linear. The sp2 is trigonoplanar. sp3 is tetrahedral. All based on the number of groups. Next carbon. How many groups? You should see 3 again. A double bond to the left, a single bond to a carbon on the right, and then a single bond to that hydrogen that's sitting on it right now. So 2 single bonds and a double. I count a total of 3 groups. That's sp2. Next one. That carbon. You should count 4 groups. That carbon is bonded to the carbon on its left and its right. Okay? And there's 2 hydrogens on it. That's a total of 4. Carbon to its left, carbon to its right, and 2 hydrogens on it. Total of 4. 4 groups is sp3. It's a tetrahedral. Next one. How many groups? Should see 2. A triple bond on the right, single bond on the left, and it's the carbon on the left, even though it's not drawn in. It's 2 groups. That's sp. Likewise, this is sp. Let's skip that one. We'll come back to oxygen. It's a little more thinking. Carbon, right there. How many groups? Should count 3. A double bond going up the oxygen, single bond to oxygen on the left, and a single bond to carbon on the right. Total of 3 groups. sp2. Okay. Next carbon, how many groups? This says CH2 if you can't see it. Yes, 4 groups, single bond down, single bond right here to that carbon, and then there's 2 more hydrogens on it, total of 4. This is sp3. Okay, now let's tackle this nitrogen, I guess. This is a little more thinking. How many groups on that nitrogen? It's not 3, but it looks like it. There's 4. There's a single bond up. You see that one? That's 1. And you see there's 2 hydrogens on it. That's 3. What's the 4th one? There's an undrawn lone pair here. Oh, the joy of learning that. Why does a lone pair have to be there? Anybody know? Because what is 0 on that atom? 2 words. The formal charge on that nitrogen in every atom here is 0. Thus, you need a lone pair on it to make a neutral. And I'll give you a general hint. Every nitrogen, if it has a formal charge of 0, will always have a lone pair. But we don't always feel the need to draw that lone pair because we think it's obvious. Okay? Now you know, so it can be obvious to you. A nitrogen will have a lone pair if it's neutral, formal charge. Okay. How many? Oh, so this is 4 groups sp3. It's tetrahedral with 1 lone pair would be trigonal pyramidal. Okay, how about this oxygen right there? How many groups? Think along the same lines. 4 groups. There's a single bond to carbon on its left, a single bond to carbon on its right. That's 2, and the other 2 are lone pairs. Because to have a 0 formal charge, we need 2 lone pairs on any oxygen. That's it. 4 groups, sp3, tetrahedral, or bent. Okay, so here's the other hint. All oxygens, if they have a 0 formal charge, will have 2 lone pairs. That'd be good to remember. So thus, this oxygen has 2 lone pairs as well. But we don't do hybridization for anything that's not central. Or it needs more than 1 group on it, really. Okay, any questions, or do you want me to redo any of these? I'll say one more thing about it. Notice, and if I'm kind of thinking about this right here for a moment, from before. So that's it. With that in mind, notice that carbons with single bonds are sp3 hybridized. Do you notice that? Carbons, except for one of them, with double bonds are sp2 hybridized. And carbons with triple bonds are sp3 or sp hybridized. You notice the pattern now? So single bonds, you're going to get an sp3 with carbon. You got one double bond on carbon, that'll be an sp2. If you got a triple bond on carbon, that'll cause you an sp. Okay? So the only kind of funny one here is this one in the middle. 2 double bonds will also cause an sp. All right, are we ready to move to the next one? Okay, this is a typical problem for a final. Got that? Very typical. Let's do another one. Caffeine, your favorite, keeping many of you awake right now as we speak. This is also a very common problem for a final. Okay? All right. We want to know the hybridization of pretty much everything we can get. Okay. Let's do some of the ones that will hopefully be easier. There's a carbon right here. Okay, remember in every vertex there's a carbon. What's its hybridization? Well, maybe I'll start. How many groups? 3, so it's sp2. Just follow the table. 3 groups, sp2. There's a carbon right here. It's also 3 groups. 1, 2, 3, sp2. Same for this carbon right here, sp2. And this carbon right here, sp2. Okay? Oh, how about this carbon down here? How many groups does this one have? Oh, right there. 4, because there's 3 hydrogens and 1 single bond to nitrogen. 4 groups means sp3. Let me zoom in on the control a little bit, just so it's easier to see. Okay. All right, let's work on some of the others now. That nitrogen right there, how many groups? From what? I just told you there's 4. Remember, there's a lone pair. So a lot more of them have lone pairs. This one would, and this one would. And it won't be relevant to us, but these oxygens will have 2 lone pairs. Again, to save ink, we usually don't draw those. So if you look in the literature, look in other places. Oh, and there's one more nitrogen right here. They don't always draw the lone pairs for you. Okay. So this nitrogen also has 4 groups. This is also sp3. This one also is sp3, that nitrogen right there. This one, though, is what? This nitrogen right here at the bottom right. Yeah, 3 groups sp2 because of the double bond. Okay, but notice it's neutral, so there's still a lone pair there. Okay, did I miss any nitrogen? I missed this nitrogen. sp3, 4 groups for that nitrogen, so it's sp3. I think I got all the nitrogens. Let's see. Oh, this carbon, these 2 carbons both have how many groups? 4, so they're also sp3, just like this one down here. Let me write that for you. sp3, sp3. Okay? All right. There's 1 atom left that I think I haven't got. If I got all the other ones, it's that one right there. How many groups does that atom right there have? 3. Nice. How come I only count 2 though? 1, 2. Where's the 3rd group? 3 is the correct answer. Right. There's an undrawn hydrogen right there. What? Oh my gosh. That's crazy. Who's drinking the Kool-Aid? I knew this would be an issue. That's why I told you on page 13 of the reader. And in the beginning of chapter 3, if you want to refer back to this, this is literally the reason I told you this. You need this in OChem as well, but this is the place you need it for our class. Every neutral carbon has 4 bonds. That's the key. Every neutral carbon, and that's one of them, there's a carbon right there, has 4 bonds. 1, 2, 3 is all you count here. And when you don't see the 4th one, that 4th one is an undrawn hydrogen. So if there's ever a bond missing on the carbon, it's a hydrogen that should be there. Okay? Every carbon must have 4 bonds, and that's what you see on the top of page 13 of your reader. Okay? That is, I believe, the only carbon that was missing 4 bonds, so that's the one. Okay. Any questions on that? Say it again. Explain it one more time. Okay. For a carbon to have a 0 formal charge, it must have 4 bonds. Notice what we did earlier. We've always done it, you've just never noticed it. 4 bonds, 4 bonds, 4 bonds. It has to because it's in the 4th column of the A part of the periodic table. So, I come up, I'll just move this to make it less messy. I come up to this molecule right here, and I see a carbon that's at this vertex right there. And I wonder, why does it have 3 bonds? Because the printer needed to save some ink and toner and did not draw that last bond. And that happens all the time in OChem. All the time, all the time. So, if there's ever a missing bond, you need to fill it out with hydrogens. So it's assumed, the drawer, the artist, assumes you know that. Okay? Okay. So, oh, this has how many groups now? 3, so it's called sp2 hybridization. sp2. Earlier, it looks like this. You might want to have this handy. Just have that handy. We're going to do this for caffeine. What you want to know is that every bond has a sigma bond. So to count the sigmas, we're going to count every bond. To count the pi bonds, we're going to look for double and triple bonds. Let's do that first. That's easier. Remember that every double bond contributes 1 pi, and every triple bond contributes 2 pi's. So, how many pi bonds do I have here? How many double bonds do you count? 1, 2, 3, 4. So there's 4 pi bonds. 1 pi for every double. Okay? The pi bonds are usually the easiest to count. The sigmas are easy because you're just counting, but you have to count every single bond. I'm going to give you a little head start. Let's count every single bond. You can do it with yourself, by yourself, or with a partner. I need to count up how many total bonds are in this molecule. I have to do it too because I can get it. So that molecule, total number of bonds. Lone pairs don't count as a bond, so just bonds, literal bonds. Yeah. Okay, so I'm ready, I think. Anybody have a number greater than 15? Yeah, anybody have a number greater than 20? Okay, what do you get? 26, 24, it's somewhere around there. Yeah, I think it's 25. You didn't count 25? Okay, let's just count. Maybe I'm off. Maybe I'm wrong. Let's see. Doesn't matter. We graded the valuations. I can be wrong now. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Then let's go around. 11, 12, 13, 14, 15. Is that okay? 16, 17, 18. Yeah. 19, 20, 21. 22, 23, 24. Oh, there's a hybridization. 25. Wow, that was exciting. I'm glad we did this after. It's just counting. You just got to be diligent about counting. This is probably as hard as it gets. But I would consider this a medium difficult question for the final. So that was, what did we say, 25? I think I counted 25, right? Okay. Since I was so excited, let's try a couple more of those. Here's a slightly easier one. Just want to make sure you can do it. This one right here. That one right there. How many pi bonds? 2 pi bonds. How many sigmas? 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Is that okay? Let's try one more. This one. That's an HC. HC. It got full stamped on the unfortunate part. Okay. How many pi bonds in this molecule? You should count 1, 2, 3, 4. That counts as 2. So 1, 2, 3, 4. How many sigmas? I have to count 2. I don't remember. What do you get? I think I got 8. Let's double check. 1, 2, 3, 4, 5, 6, 7, and there's a hydrogen there, 8. Any questions on these? This is a very normal type question for a final. Any questions on that? Yes. If I'm counting sigma bonds, the asking person up here is asking, how do I count? Each bond counts as 1. A triple bond counts as 1. A double bond counts as 1. A single bond counts as 1. Is that okay? And I'm just following the table that I gave you earlier. that looks like this. All these count as 1 sigma, but the triple bond counts as 2 pi's, the double bond counts as 1 bond. Okay. This is the key table right there for counting. Did you want to do one more?
Yes.
One more. How many pi's? 3. 1, 2, 3. How many sigmas? Not 6. What's here? Remember, every carbon has 4 bonds. Okay, one more. Last one. I've got other stuff to do. How many pi's? 1, right there. How many sigmas? Think about it this time. Think about the hydrogens. How many hydrogens are here? And here's 1. How about here? How many bonds total should I have? 1, 2, 3, 4, 5, 6, 7, I believe. 8, 9, 10, 11, 12. Is that right? Remember, every carbon has 4 bonds. Okay. I gotta move on. We can do more during the review session. Okay. All right. Okay. What's missing, by the way? What's missing? Hydrogen where? Okay, get used to that stuff. Okay. By the way, how many sigma bonds? 8, right? Okay. One other thing is we could ask you, let's call this carbon 1 and carbon 2. What bond makes up carbon 1 and 2? Okay. Or what hybrid orbitals overlap to make the carbon 1 and carbon 2 bond? First of all, would that be a sigma or a pi bond? That's a sigma. Okay. Carbon 1 has what hybridization? sp2, because it has 3 groups, and carbon 2 has what hybridization? sp3 has 4 groups. 1, 2, 3, 4. This one has 1, 2, 3 groups. So the hybrid orbitals that overlap are the sp and sp3 to make that single bond. That's another type of question. Okay, so we'd ask you what overlaps to make that bond. The sp2 from this one and the sp3 from that one. Okay? Another very common question.